All right, there are a couple more things we need to know about waves, and at least the first one is something that we know already, maybe without identifying it with Physics 106, and that is waves can reflect. So when we have a wave traveling through space, or through a rope or through the air or whatever medium it's traveling through, when it runs into some boundary, it reflects and creates a wave that is going back in the other, in a different direction. And that boundary could be a change in the medium. It could be a place where the density of the air changes, or where it goes, in the case of light, if it goes from air to glass, you can get a reflection from that. Or it could be the end of your system. So like your string goes, and then your string ends. Well, you can get a reflection off of that change from string to no string also. So waves reflect when the system changes or ends, wherever there's a boundary. I guess I should say where the system changes or ends. So, in other words, very often when you're creating waves and sending them in one direction, you end up with waves traveling in both directions because of this reflection. So I'm over here shaking this end of the string, I'm sending a wave, down to the other end of the string, and where the string ends, there's a reflection generated, and so there's another wave also oscillating that's traveling back the other direction. Okay, so this is not a good picture. We will have better animations to show you that I'll link to somewhere, so you guys can kind of visualize what I mean by this. Okay, the other important fact about waves is that these waves obey superposition. So this word superposition means that when we have more than one wave in a system, the total displacement of the system is just the sum of the individual waves making that up. So in other words, if I have a wave traveling this way through my system and I have another wave traveling this way through my system, the total displacement of my system, like how far the string is from equilibrium and all those different points, is just one wave plus the other wave. So in other words, all this is saying is the displacements of multiple waves simply add at their particular points in the medium. This also has the effect of two waves that meet each other just travel right through each other as if the other one isn't there. They don't affect the motion of each other. These types of waves cannot reflect off of other waves. So superposition means both of these things because mathematically they're the same. Okay, and there are some good animations to visualize both of these that I will link to later on. Okay, so this brings us to our next idea, which is standing waves. So if we have a medium like a string with a wave in the string traveling to the right. So I have all this, I'm over here going like this and making a wave going to the right. It is possible I will get a reflection that is traveling to the left. Now it turns out if we just take this superposition thing and we say, okay, I have a wave like this and I'm going to add to it a wave the same amplitude but traveling in the opposite direction, I end up with something very very interesting. So this wave plus this wave equals, so this one is traveling to the right, this one is traveling to the left. If I add this wave going to the right to that wave going to the left, I end up with a wave that is not going to the right or to the left. It is at a particular instant in time, and this is hard to do without animation, so again, I will link to something via email or Canvas or something. I'm going to get a wave that looks like this. So here's my, here's what my wave looks like at a particular instant in time. But rather than these peaks, these ones are all sliding to the right, these ones are all sliding to the left. These ones are staying put where they are, and they are just oscillating up and down. So at one moment, my string is going to look like this. At another moment, it's going to look like this. At another moment, it's going to look like this, and then maybe like this, and then maybe like this. And so these different places on the string are just oscillating up and down, and we don't see any visible wave moving to the left or right because it is like an equal mix of to the left and to the right. So anyway, this is called a standing wave. So called because it is, not moving to the left or to the right. It is like it is standing still, although still oscillating in its amplitude up and down. Okay, so our standing wave, now note, both of these waves still have the same wavelength. And if I wanted to mark that on here, my wavelength of this top wave is like this. This is my wavelength lambda. That's the same as for my wave on the bottom. This is also lambda. So this wave down here has that same wavelength lambda. It also has the same frequency, right? These have a frequency and a velocity associated with them too. This wave has that same frequency as well. Okay, so standing waves, well, there are a couple more like anatomy things about standing waves that we should point out here, I guess. So on our standing wave, we have these places where our displacement is zero. So even though our wave is like moving up and down, there's a place on the string that's not moving up or down at all. Things around it are moving, but this string right there is not. So these are called nodes. And at those points, our displacement is zero. So there's another node right there. We also have some places where our displacement is maximum, right? So here, our string is moving, the most. It's moving all the way between these 2 points. So this is where we have, here and here and here. I'm just marking this one because it's over to the side. This is where we have the most displacement. This is uncleverly called an anti-node. So this is the place on the standing wave where we have the maximum displacement. All right, so if we have a picture of what a standing wave looks like, we can look at it and say right away, oh, these are the nodes, these are the antinodes, and this will be a helpful thing to be able to do. Also, note that our wavelength here is marked between these 2 nodes, right? That's the distance between this point and this point. So it turns out the convenient rule of thumb for the wavelength of standing waves is the distance between 2 adjacent nodes is half of a wavelength. So let's write that. So the distance between any 2 adjacent nodes, these two, is half a wavelength, lambda over 2. But not these 2 because they're not adjacent, right? These are a whole, there's a whole other node in between. You can also do the same thing with antinodes, right? So the distance between this antinode and an adjacent antinode is also lambda over 2 is also half a wavelength. So we can write 2 adjacent nodes or antinodes. So this is a very useful rule for solving these solving these standing wave problems. All right, so why are standing waves so important? So it turns out that we get reflections from the ends. We can get reflections from the ends of our system, like where our string stops or where our air hits the wall in the room or something like that. And when that happens, that can create a node or an antinode at that location. So in other words, if we're looking at a longitudinal wave like sound and we're looking at how the air molecules are moving, a node would be where the air molecules are not moving. The wall is going to keep those air molecules from moving. The wall is going to the wall is going to force the air nearby to be a node. That air cannot be displaced into the wall, right? The wall is going to stop it. So that creates a node at that wall for all sound waves. So I have another wall over here that also has a node. And what that's going to do is that's going to force the standing waves that are allowed to exist in that space. And we'll have another full video about this, but I just want to prime you guys with the idea. So if we have a system where we're saying this end has to be a node and this end has to be a node, that is going to limit what the standing waves look like that we're allowed to have. And in particular, it's going to limit the wavelengths and frequencies of those standing waves. So in other words, I can't just have any old wavelength here give me a standing wave. If I pick something like this, this wavelength is never going to be able to give me a standing wave with a node here and a node here. I can have a standing wave, however, with a node here and a node here if my wavelength is this, if my wavelength is exactly the distance between those two, because then my standing wave pattern is going to look like this. Or I can also have a node on either end if my wavelength is longer, if it looks like this. So my wave, if I were to continue drawing my wave, this is like the first half, the second half would go over there somewhere. Anyway, we'll deal with some numbers for this in the next video, but hopefully that gets you thinking about why standing waves are important, and this is going to connect them to resonance, which is a very important idea in physics.